Welcome to the 8th lesson in Area of Study 3. Today we'll be having a look at time dilation and length contraction, and yes, presented by me. Typically a much more difficult part of special relativity, and a lot of students struggle with it. So if you do have questions at the end, you're more than welcome to send me a session request on airlearners.com, find me on the tutors page, and yeah, let's get started. Okay, what are we going to do? So first thing we're going to have a look at is muons, which are a subatomic particle. Then we'll take a look at time dilation and length contraction, and we'll do some work with calculating velocity. Right, so the important things to note just before we start is that velocity is a constant in all frames of reference. What that means is that if I measure your velocity and you measure my velocity, then if we have no indication of external movement, I suppose, so we can't tell which one of us is moving, then we'll each measure our velocities to be the same as the other person. In the frame of reference of the fast-moving object, the time is the proper time while the length is contracted. That is only for when they're measuring something in their own motion. And in the frame of reference of the stationary observer, the time is dilated while the length is the proper length. It is a very tricky concept to grasp. However, you can make a table that shows what measurements and what, I guess, symbols used to describe which one is the proper time, the proper length, and the contracted length and the dilated time. Muons. In the muons frame of reference, which travel at a very high speed, close to the speed of light, the distance to the ground is smaller than the proper length due to length contraction. So this is kind of an application of our knowledge from the previous slide. As the speed of the muon is a constant in all frames of reference, the proper time to travel to the ground is less from the muon's frame of reference. So what that means is that from a scientist on Earth, they will measure the dilated time, which is a longer period of time. So they expect that because of the half-life of a muon, because it's a subatomic particle, has a half-life, and so they will measure more muons than reach the ground because in the muon's frame of reference, there's less time that elapses. So those muons are tiny particles that form in the upper atmosphere at relativistic speeds. They have a short half-life. However, as they feel like there's a shorter distance than the proper measurement by a stationary observer, more of them reach the surface than would be predicted under Newtonian mechanics. This revelation is evidence that can be used when describing special relativity. It's quite common on exams and assessments. Using the Lorentz factor. So this is where the Lorentz factor can be applied for useful calculations. These are our formulas that we use in special relativity. I have gone with the convention of putting a 0 as a subscript for the proper measurements, and simply the letters were appropriate for length and time. Gamma, which is the other symbol here, and here, all of these, that's the Lorentz factor. If you need a refresher on that, then you can have a look at the previous lesson, lesson 7, which deals with an introduction to special relativity. So here we have the proper time is the dilated time divided by gamma, and you can rearrange that so that the dilated time is the proper time multiplied by gamma. So that's that first or second dot point on the page. Third dot point, the proper length is gamma times the contracted length. And again, you can rearrange it so that the contracted length is the proper length divided by gamma. All of these are scalar measurements. Because we're measuring length rather than displacement, there's no need to put any directions. Finding velocity. So we can use the fact that the speed is the distance divided by time. That's just something you should know even from maths, not necessarily physics, to find the velocity to show that in both frames of reference, in both the fast-moving and stationary frames of reference, the velocity is the same. So we have these 2 points here in the frame of the observer. Let's say we have the proper length divided by the time, and in the frame of the fast-moving object, we have the contracted length divided by the proper time. We can see that from our experiment per se with our muons. So we start off with the frame of the observer, and we can make that dilated time in terms of proper time. So we can put a gamma in there, like so. Then we can separate out the proper length divided by gamma, or the Lorentz factor, which is exactly what we get for length. So this formula here, same as that. I'm essentially saying, well, that bit multiplied by 1 on the proper time between there and there. So with that, we can simplify that fraction, and we get the proper length, the contracted length divided by the proper time, which is exactly that over here. So essentially what we've done is we've gone from here to here, and that way we can say that the velocity is the same in all frames of reference. Okay, let's have a look at a practice question. Number 1, a stationary observer sees a spacecraft traveling at a constant speed of 0.97 c. The observer measures the distance covered over a time interval to be 10 kilometers. Calculate the distance traveled from the frame of reference of the spacecraft and the proper time for this to elapse. So there we go, there's a nice diagram of what's occurring. Make sure that you keep in mind that c is not just any letter, it is the speed of light. So it's 3 marks, so you've got about 3 minutes to do this question. Should take you a little bit less, but you can pause the video and get back to it once you finish. All right, now that you've had an opportunity to do that question, let's take a look to see how I would approach it. First thing I would do is calculate the Lorentz factor. So that is the formula that we have seen in the previous lesson. If you looked at it, if you haven't, then I would recommend going to look at it now because it is quite useful in these questions that we will do in this lesson. Simply substitute in our value of the speed, which is 0.97 c. The c squareds will cancel from the numerator and denominator, and so you're just left with 1 on the square root of 1 minus 0.97 all squared, which means we get 4.11 as the Lorentz factor. Our proper length is 10 kilometers. That's the scientific notation for it. And our contracted length, which is what it will be from the frame of reference of the spacecraft, is going to, and then from there we can say that the contracted length is 2,431 meters. Now that is 4 significant figures, so then when we finish off our answer, after we find the proper time to elapse, then we will shorten that to 2 significant figures. From there we can find the proper time, and we can use the values that we already have here. Try to use the most exact values, which is why I've put in that full number over there. And then you can just rearrange for the proper time and you get that value there. Again, that's 4 significant figures, not 2. So our answers are going to be, the length is 2.4 by 10 to the 3 meters, and the proper time is 8.4 times 10 to the negative 6 seconds. So that's quite a long question for 3 marks. In terms of mark allocation, you definitely get 1 for that, 1 for this over here, and probably 1 for finding the Lorentz factor. If you don't shorten it to the correct number of significant figures, usually you just lose 1 mark. All right, practice question 2. Spaceship X01 is traveling with a Lorentz factor of 9.68. Find the velocity of this spaceship in terms of c, the speed of light in a vacuum. 2 marks. Got a couple of minutes to do this. You can come back once you have finished. All right, now that you've had an opportunity to do that question, let's take a look to see how I would approach it. First thing, again, is to use our Lorentz factor formula, and with that, we are going to try and solve for v. So what we're going to do here is we are going to square both sides and then invert them. So what I mean by that is where you raise everything to the power of -2. So everything here, power of -2, gives us this value here. From there, we can quite simply -1 from both sides and also multiply by negative. And again, it's fairly straightforward, but then multiply up the c squared. From that, we square root both sides, and we get this formula for velocity. This is quite useful. You may want to put this on your cheat sheet. Simply substitute in the value of the Lorentz factor, and you get v equals to 0.995 c meters per second. That is to 3 significant figures, because the only thing we have here is in 3 significant figures. So that would be how I would answer that question. In terms of mark allocation, probably get 1 mark for this and 1 mark for that. Okay, practice question 2b, a little bit of a long one. Spaceship X01 passes another Z99 that is stationary relative to X01. The commander of Z99, Daniel Shub, notices that the length of X01 in the direction of motion appears to be just less than 1/10 of the length that it should be, and is worried for the crew's safety. Explain with reference to the term length contraction and with the aid of relevant calculations why Commander Shub should not be concerned. 4 marks. Note that there is both a bit of calculation involved and explanation, so it should take you about 4 minutes. Pause the video and we can have a look at the answer in a moment. Okay, now that you've had an opportunity to have a go at this question, it is quite a difficult question, but we will see how we go. All right, so let's just say that K is the proper length of X01. This involves a bit of algebra, and we aren't ever given a proper length. It just simply says that it should be just less than 1/10. So the proper length is K. Now, the contracted length, which is what the observer that's what Shub notices, Commander Shub, is going to be K on gamma, which is K on 9.68, which is roughly 1/10. So this is what I would add. As the observer that is relatively stationary to the fast-moving object, Commander Shub will observe the contracted length of the spacecraft. Hence, the length of the spacecraft will appear squashed and at just less than 1/10 of its proper length. Hence, there is no reason that Commander Shub should be concerned, as the effects are simply due to the observations of special relativity at near light speed motion. So in terms of mark allocation, probably get a mark for your relevant calculations. And the rest, the 3 marks, should include something like a statement on stationary and fast-moving objects, which is this first sentence here, and the observation of contracted length. So then you apply what you've learned from your calculations there, and then say whether they should or shouldn't be concerned there. Those are your 4 marks. All right, on to practice question 3a. On a spaceship traveling past Earth at relativistic speeds, an atomic clock records the time taken to travel a certain distance, as measured by a scientist on Earth. At the same time, an identical atomic clock on Earth records the time taken for the spaceship to travel the distance. With reference to the term time dilation, explain which clock will show a shorter elapsed time. 2 marks. Should take you a couple of minutes at least, because it is an explanation question. So pause the video, do the question, and you can click play when you are right to go. All right, now that you've had a good opportunity to do that question, let's take a look to see how I would do it. Now, one big slab of text here. Given that the distance is measured by a relatively stationary observer of the fast-moving spaceship, the principle of time dilation will occur. In the frame of reference of the spaceship, the proper length to the end of the distance will be contracted. As velocity is a constant in all frames of reference, the time elapsed on the atomic clock on the spacecraft will be the proper time, and that on Earth will be the dilated time. Therefore, the clock on the spaceship will show a shorter elapsed time. And it's a very similar question in some ways to the explanation given on muons at the very start of this PowerPoint. So it's important to be able to apply that knowledge to other situations, and atomic clocks is also a pretty popular option for assessors. In terms of mark allocation, this is probably a little bit more difficult to mark, but as long as there are a couple of valid points and you mentioned something along the lines of which one will be dilated and proper, so this point over here, and give a conclusion, that would be 2 marks. It is always good to mention this first bit about proper length and contracted length, because that kind of links the two, and mentioning velocity gives you that full spectrum that you need to answer a question well. Let's just have a quick summary of time dilation and length contraction, because I think it is really important that you understand it. It is a very complicated subject matter, and the fact that it is so complicated is, I guess, validated by the fact that it is a university subject. People do PhDs on special relativity, so it is very much a complex topic. So a remote observation of length will result in a contracted length. So let's say I'm measuring you moving quickly, then I will accuse you of being shorter than what you measure yourself to be. That is the principle of length contraction. And dilation, time dilation is about, so a remote observation of time. So I'm measuring you moving, and I will accuse you of traveling that distance slower than you think that you have. And I'll accuse, for instance, your clock of running slow. So those are the 2 principles, I guess. If you have any queries, then this slide should help you out. So if you need anything else to help, you can consult your teacher. Sometimes if you've got a great teacher, which hopefully you do, then you can ask them and hopefully they'll be able to explain it. You can contact me for a session and we can have a look at it quite in depth. We can spend as much time as you need on it. And then finally, you may be able to look at your textbook. Now, textbook explanations aren't always amazing, but they can often provide a little bit of a helping hand where necessary. So those are kind of the 3 options that I would consider. I wouldn't look, for instance, YouTube videos, etc., because they often are targeted at a different level. So sometimes there'll be university lectures, for instance, which will probably go straight over your head, or otherwise they are explanations given to much younger kids. So you want to have something that is directed exactly at the VCE study design, and the best place to do that is to speak to either your teacher, you can contact me, or your textbook. All right, just a very brief review of our quite complicated lesson. So we had a look at muons, those little particles. Time dilation and length contraction we did for most of the lesson. We looked at using the Lorentz factor and using velocity as a constant in all frames of reference. The next lesson and the final lesson of content for a review lesson in Area Study 3, we'll take a look at mass energy, and that includes relativistic mass, momentum, and some good graphs. So thank you very much for your attention. I hope that you found this lesson interesting and that you learned something new. If you'd like to get in touch, feel free to go to the airlearners.com page, and you can find me in the tutors section of that. Thank you very much for your attention. I'll see you next time.